So welcome everyone. We are very happy to have Dr. Sthitadhi Roy from University of Oxford for today's speaker. And Sthitadhi gave a very nice introduction to this, the idea of dynamics in quantum many-body systems yesterday, and what he's going to do is elaborate on some of these issues in context of his work today in his talk on Fock-Space landscape across many-body localization transition. So, what do you?
Thank you, Shubhru. And thanks to all of you for tuning in. It's very nice to see you again. And for those who attended yesterday's talk, I hope that I gave an idea of why do we care about ergodicity breaking in the context of many-body localization in isolated quantum many-body systems. And what I'm going to do in this talk is talk about this phenomenon of many-body localization and an associated quantum phase transition from the Fock-space perspective. I'll elaborate on what each of these terms mean in a reasonable amount of detail as we go along. This is a board talk, but I'll work out several things on the shared Blackboard, but I'll also have some figures which I have embedded into the slides. So I hope we can work through that. Okay, so this talk is based on these two papers mainly. One of them is still not out yet. I mean, we are put it out very soon. But I should also mention these three papers, which sort of informed a lot of ideas and helped us sort of have a bigger picture of this Fock-space landscape across the many-body localization transition. So let me start with an outline of my talk. Now, I'll start with a somewhat pedagogical introduction to many-body localization, as in what is the phenomenon. I talked a bit about it in yesterday's colloquium, but I'll give out some more details about this and try to motivate why do we care. Then I'm going to give a picture of many-body localization on the Fock-space, and the main question here will be why we go to the Fock-space and what do we gain from it. Then I'll come to the most important part of my talk, which would be about the nature of the MBL phase and the MBL transition from the Fock-space perspective. I'll try to motivate a scaling theory of the many-body localization transition based on some quantities which are defined on the IPR, and argue that there are some formal similarities to possible Kosterlitz-Thouless-like scalings near the transition. And finally, I'll very briefly discuss that why, even though we are looking at this problem on the Fock-space graph, this is not really an Anderson localization problem on a high-dimensional graph, but rather the presence of correlations in the effective Fock-space disorder make it a very unconventional problem. Okay, so this is the plan of the talk. And let me start with a very basic introduction to many-body localization. And to do that, I'll go back to its roots. And the root of MBL lies in Anderson localization all the way back in 1958, where Anderson basically showed that if you have a set of non-interacting quantum particles hopping on a disordered lattice, the disordered, say, is in some on-site potential, then the eigenstates are exponentially localized. Now, this was sort of a very, very important and stark result back in the day, and it sort of this entire field of localization continues to be one of the most active areas of research in modern condensed matter and statistical physics. So soon after Anderson's work, it was shown that in low dimensions, and when I say low dimensions, I mean d less than or equal to 2, it was shown that even an infinitesimal amount of disorder basically localizes your system. And one of the sort of first works on this was by Sir Neville Mott. And this was sort of an important result because there was a lot of interest back then in low dimensional systems in the context of transporting quantum wires and so on. Now, the question of many-body localization is what happens when these quantum particles actually start interacting with each other. they could interact via some density term, or it could, and the interaction generally is short-ranged. So that's the setting we will consider. So there would be some short-ranged interactions between these localized quantum particles. And the question would be that, does this localized phase persist all the way up to a finite interaction strength such that we have a many-body localized phase? And if we actually do, then do we have a bona fide phase transition as a function of, say, disorder strength, or as a function of interaction strength? You can go this way or this way on the phase diagram. And is there a bona fide phase transition in here? And if so, what is the nature of this phase transition?
Sorry, Sthitadhi, to interrupt, but just to make sure I understand, I can think of the disorder strength as roughly speaking the amplitude of this random potential, the VFR.
Absolutely. So imagine that I have a lattice, and on each side I have some potential which is, say, drawn from some distribution which has a width, uniform distribution which has a width from minus W to plus W, and the disorder strength would be then W. Okay, and one thing that I should clarify is, in all of the in the rest of the talk, what we will consider is that the distribution of these disorder potential, or disorder, it could be also disordered couplings, they will be well-behaved distributions. So they will have generally, they will not typically have, say, power law tails and so on. So we'll consider either uniform distributions or normal distributions for the disorder strengths, disorder potential, sorry. Okay, so the questions therefore are about the nature of this MBL phase and the possible phase transition in here. But even before we get to that, you might ask that, why do we actually care about many-body localization, and why is it a fundamentally new thing to worry about? The reason this is a fundamentally new phase of quantum matter is because this is incompatible with conventional statistical mechanics and equilibrium thermodynamics. And just to elaborate on this point, let's recall how isolated quantum systems exhibit thermalization or are compatible with equilibrium thermodynamics in general. So what happens is, suppose this is my isolated quantum system, and this has several of these subsystems. Now, in an isolated system, what happens is a typical subsystem, or any subsystem for that matter, is going to very efficiently communicate with the entire system. So the large system acts as a bath for this small subsystem, and thermalization happens locally. Now, if you take a picture of a localized system, then you can say that, well, each particle is localized, or the wave function of each particle is localized in some small region, and say any particular region can talk efficiently only to some subsystems which are nearby to it. So as a result, this entire mechanism of the entire system acting as a bath for a subsystem fails, and many-body localized systems do not show thermalization, and hence fall outside the conventional paradigms of thermodynamics. So a crucial distinction is that thermalization happens in ergodic systems. It doesn't happen in many-body localized systems. This is actually equivalent to saying that, if I start with some non-equilibrium state, then at long times, an ergodic system is completely going to forget what its initial condition was and equilibrate to some thermodynamic state which would be consistent with, or the temperature of which would be consistent with the energy of the initial state. So there is naturally no persistence of memory in ergodic systems, whereas in a many-body localized system, the system is going to remember its local configuration to some extent for infinitely long times, and hence there is a persistence of memory in MBL systems. And finally, there is the notion of quantum entanglement, because you can visualize this web of non-local correlations as there being a large amount of entanglement in the system, because these non-local correlations precisely encode that. So what happens is a typical eigenstate of ergodic systems taken from taken from the spectrum of an ergodic system, which lies or whose energy lies in the middle of the spectrum, so very high excited states, they typically have what we call a volume law entanglement. So the simplest way of understanding this is, imagine I take this system and I split it into two parts that I'm trying to denote by this black line. And basically you can see that there are these lines of correlations going through the entire system which cross this cut. So naturally, the amount of entanglement or the amount of correlations that is there in this system is proportional to the entire volume of this system. And typically, the entanglement does indeed go as L to the power D, where D is some dimension. On the other hand, if you consider the same situation in a many-body localized system, what really happens is the two parts of the system now that I have gotten by dividing it into two parts can talk to each other only sort of via the degrees of freedom that sit close to the cut, close to the boundary. As a result, the entanglement that or the entanglement between the two parts of the system is proportional only to the length of this boundary, and that is precisely what we call area law. And that goes as L to the power D minus 1. So this is a qualitative distinction between ergodic and many-body localized systems, and these sort of tell us that many-body localized systems are indeed a new phase of quantum matter. Now, of course,
sorry, I have a question. Sorry, I joined a little late, so I missed something. On the left-hand side, were you referring to the entanglement between the two systems, or just to the entropy of the two parts?
I'm quantifying the entanglement between the two parts of the system via an entanglement entropy.
I see, but is the whole system in a mixed state, or is it in a pure state? You're saying
no,
that
the whole system is in a pure state. Of course, if the whole system is in a mixed state, then I'll have to do something more sophisticated to distill out the classical entropy before I can talk about the quantum entanglement. So
I see.
Yeah.
I see. It's in a mixed state, it's in a pure state, but it's still in a pure state that's at a finite temperature. So in the vacuum, you would still expect an area law on the left-hand side, but this is in some highly excited.
Right, exactly. So in fact, these are at finite energy densities and what we often colloquially call infinite temperatures.
Fine. Okay. Thank you.
Okay. So now a rather remarkable point about these many-body localized systems is that their properties are robust. In the sense that if you slightly change the parameters of your system a bit, if you slightly increase some coupling or add some term to your Hamiltonian, which is still, say, short-ranged and doesn't sort of change, say, the dimensionality, or you don't change the dimensionality of the system remains many-body localized. So this is another sort of point of distinction between this kind of an ergodicity breaking and, say, what you have in integrable systems, because integrable systems are sort of special, but many-body localized systems are robust in breaking ergodicity. So with this picture or with this sort of physical picture of an MBL system, let's lay down that what are the central questions in the context of MBL. So the first is that.
Can I just slow you down? Just the previous slide again, if you don't mind. So you listed these three properties and contrasting the behavior between ergodic and MBL systems. But I was just wondering, to what extent are these three features completely independent in some ways? For instance, does persistence of memory come always together with an area law, or is it can they be logically distinct? It may not apply to what you're going to say about the MBL systems, but are there other possibilities? Thermalization, I can sort of see. Of course, there is the integrable systems which don't thermalize, and they are probably different from these, but especially the latter two, I just was wondering.
Yeah. Okay, so that actually is quite a subtle question, because even in these many-body localized systems, the statement that I made about the area law is true for arbitrary eigenstates of an MBL system. However, you can say that suppose I prepare an initial state which has zero entanglement. Say I prepare some product state, and I let the system evolve. Now I would say that, well, the system, of course, if it's in an MBL phase, it's going to have persistence of memory, and the local configuration is going to survive for an infinitely long time to some extent. However, that does not mean, that does not mean that the entanglement of an MBL system is not going to grow. What actually happens is that in many body localized systems, say following what we call a quantum quench, the entanglement entropy between two parts of the system actually grows logarithmically with time, but it saturates to a volume law. Whereas, so basically, if I take T to infinity, then it saturates to a volume law. Whereas in the ergodic systems, typically the entanglement entropy goes as, with some power, let me call it T to the power alpha. And again, if I take the limit of T to infinity, it actually goes to a volume law. So it's not obvious that one should immediately imply the other.
So, sorry, on the right-hand side, you want L to the T minus 1? I didn't understand.
Yeah. No. So so these are statements about the eigenstates of an MBL system, of an isolated MBL system. But if I actually do dynamics on it by starting from some out of equilibrium state, which has a lot of, but say, which is in a product state initially, so that the initial entanglement entropy is 0, then in an MBL system, the entanglement actually grows logarithmically in time, but eventually at infinite times for a finite system, it does go to a volume law. And how is that compatible with the fact that the eigenstates have area law is something I can discuss later on. But yes, that's really what happens. In fact, this is one of the things that distinguishes a many-body localized phase from a simple Anderson localized phase, because in an Anderson localized phase, the entanglement would grow for some time and then saturate to an area law.
I see. So, sorry, this may not be the key part if you're not, but you said you have a product state, that means product state between left and right, right? But you could put the left in some energy eigenstate and right in some eigenstate if there was some, approximately local Hamiltonian. And then the left, so then it confuses me a little bit, because it seems that a lot of these blobs on the left-hand side that you have would kind of, never develop correlations between things on the right-hand side. I can see that in the middle, some entanglement would grow. So this L to the D is confusing. Is there some intuitive way to understand this final volume law?
There is an intuitive way to understand the volume law. So what actually happens is that the localized sort of, so in an MBL phase, you again have lots of conserved quantities, but you can think of these as exponentially dressed versions of the conserved quantities that you would have in the limit of infinite disorder, right? Now, and as a result, what you can do is you can write down an effective Hamiltonian for the many-body localized system in terms of these conserved quantities. So for example, you can write down an effective Hamiltonian for an MBL system in terms of, say, some spins. Let me call it tau z's. And then you can have zj, where and then you can have higher order terms as well, where these jij's actually decay exponentially with the distance. Now, another point is that these operators, tau z's, are actually superpositions of, let me write it in this way, some ci mu sigma mu I, sum over I and mu, plus I can then keep ij mu nu, ci mu j nu sigma mu I sigma mu j, and so on and so forth, where this ci of mu would decay exponentially, or rather cj of mu is going to decay exponentially with some other length scale. Let me call it psi prime. Now, you might ask that, well, if I actually now create a state, which is, say, a product state in the sigma basis, which is my physical spin basis, say, then what happens is that the tau spins are going to precess because they just see an effective field in the z direction. Now, to correlate the precession of say two tau spins at distance r from each other, you need a time which is exponentially large in r, because interaction is only via the z terms here, and that actually decays off exponentially. So because it takes an exponentially long time to correlate two parts of the system, you can say that the entanglement entropy between two halves of the system grows logarithmically in time. So that's sort of the intuitive picture.
Okay, thank you.
I have one question. This persistence of memory for MBL system, does this mean that if you're evolving your system and when it reaches equilibrium, you can trace back to its microstate where you started?
When you say microstate, what do you mean? Okay, I mean, in general, unitary quantum dynamics is reversible, right? So that's something, if I understand the question correctly, I mean, of course, if I start with any state psi and have an evolution, say, u of t, and get another state psi of t, then of course I can run it backwards and get to the same state. But I didn't quite understand what do you mean I can trace back to the same.
Like getting the same stress as like time reversal symmetry in the system of billiard balls, if you understand. So as
no,
system,
but I mean, but
system
unitary quantum dynamics is reversible no matter which phase you are in. The key point is that thermodynamics emerges in ergodic systems only locally. So suppose you evolve and then you trace out, a large part of your system, and then you look at just a small subsystem. In an ergodic system, you wouldn't be able to say what was your initial state, because once you trace out, you have thrown away all the correlations that sort of defined your state. Whereas in an MBL system, you can roughly say that suppose you start with an antiferromagnetic state, you evolve, and the state roughly remains antiferromagnetic at very long times. So even if you sort of trace away all the other parts of the system and leave just a small subsystem in your sort of consideration, then that will still have some antiferromagnetic order. But you still would not be able to reconstruct the whole initial state, because even though the system is many-body localized, there are some residual correlations pervading through the system, and which you will throw away by tracing out a part of the system.
So how in this MBL case would we be able to say that the system has reached equilibrium?
The way you can say that is basically the expectation value of some local observable in time is not going to depend anymore on time. However, that saturation value, let me call it, is not going to be what you expect from thermodynamics. So that's sort of the difference between the ergodic and the MBL system.
Okay, thank you.
Okay, so I was trying to lay out that what are the central sort of theoretical questions in this context. So the first is that, does the MBL phase and the MBL transition exist? Is it sort of a priori obvious that even if I turn on some interactions, the localized phase at very high energy densities is still going to survive? Then, if it does, then the question is, what is the nature of the MBL phase and how is it distinct from an Anderson localized system? And finally, if indeed there is an MBL phase, what is the nature of the MBL transition, or what is the nature of the phase transition between the ergodic and the MBL phase? So there has been a lot of work in trying to answer these questions, and some of the answers that we know right now are that the many-body localized phase definitely does exist in one-dimensional systems. It's somewhat unclear in higher dimensions because of technical and numerical challenges. Because at the end of the day, these are systems which have disordered interactions and are really, really far from equilibrium or any ground state. So there has been a lot of challenges in understanding this question in higher dimensions. But What we definitely know is that the system has, or disordered systems in 1D generally have an MBL phase. And here's an example of one of the state-of-the-art numerical studies on this, which shows that at a large enough disorder strength here, indeed there is a phase where the entire spectrum is localized.
Sorry, and what is the entanglement law in one dimension?
You mean for eigenstates?
For eigenstates, is there a log?
Yes, so
is there a log, or is it just constant? You're saying it doesn't care what the size.
No, it actually is indeed L to the power 0. It's not log. Yeah. Okay, so I should clarify that most of these statements would be, say, for very high energy density, so somewhere in this part of the spectrum. Now, of course, something special can happen at the ground state. So I'm not talking about that.
Okay, thank you.
If you have a gap ground state, yeah, something can happen there. Yeah. Okay, so then the question is, what is the nature of the MBL phase? And one thing that we understand is from perturbative arguments is that the MBL phase at finite disorder string is adiabatically connected to the infinite disorder limit. And this also sort of is tied to the idea that probably the MBL phase is emergently integrable. Now, let me elaborate a bit on this point. So suppose I take the infinite disorder limit, then I know that my trivial conserved quantities would be the degree, or would be the quantum degrees of freedom, so spins, which are defined on a single site. Now, the question then is that as I tune away from this infinite disorder limit to a finite disorder string, what I actually get are so-called L bits. Now, these L bits are what I had written on the previous slide as these tau z operators, which basically have an exponentially decaying support away from the site that they are defined for. And in fact, there are an extensive number of them because they are defined for all I. So these systems basically have an extensive number of conserved quantities. So when I say conserved quantities, what I mean is that these operators actually commute with the Hamiltonian of the system. And that's why there is this notion that the many-body localized phase is, in some sense, emergently integrable. And as a result, even if the system equilibrates, it doesn't do so to a thermal ensemble, but to some sort of a generalized Gibbs ensemble. Now, coming to the nature of the MBL transition, this actually is a very subtle question and has been under debate for quite a while now. But there are a few things that are sort of beginning to emerge in this context. The first is, if you take the state-of-the-art numerical studies in this field, and you use some diagnostic for your transition, what you find is that if you sort of imagine that this transition is a conventional continuous phase transition, then you get a critical exponent or a correlation exponent nu, which is approximately equal to 1. There are large error bars on this, but roughly it's 1. However, this is a problem because we also know from the Harris, Chase, Fisher bounds that if I have a disorder-driven phase transition in d dimensions, then the correlation, disorder-driven continuous phase transition in d dimensions, then the critical exponent has to be greater than or equal to 2 over d. So for these one-dimensional systems, the exponent ought to be greater than or equal to 2, which these numerical studies don't see. So there is a question there that what has gone wrong? And one of the simplest answers could be that, well, these numerical studies are on such small system sizes that you are nowhere close to the scaling limit. So let's not take that numerical studies or exponents seriously. But still, several of these numerical studies seem to get a very good scaling. So there is a question there. On the other hand, there's a parallel line of inquiry into this question via phenomenological RG treatments, where basically you come up with some phenomenological model of the MBL phase as being composed of localized regions and thermal bubbles or thermal regions, and then the thermal regions or the ergodic regions try to eat up the MBL phase. Now that actually begins to, or that actually is beginning to predict that the phase transition or the MBL transition has some similarities with Kosterlitz-Thouless like scaling, which might be the resolution to the question about the Harris-Chasez-Fisher bounds. And this is a rather important and interesting point to which I'm going to come and talk in great detail, but from the Fock-Space point of view. Okay, so these are the questions. Now, let me talk about many-body localization on the Fock-Space, and why do we at all go to the Fock-Space? The simple reason is that any many-body Hamiltonian, under some very limited set of restrictions, can be expressed as a hopping problem on the Fock-Space graph. So imagine I have a spin system in one dimension, and I have a part of the Hamiltonian which has, say, the disorder and the disordered couplings and the disordered fields, which I'm calling the diagonal Hamiltonian because I'll choose my sigma z to be the basis to write down my Fock-Space graph in. So there's a diagonal part of the Hamiltonian, and then there's an off-diagonal part of the Hamiltonian, which generates the tunneling between the many-body states. So I can, of course, write this model once I choose my sigma z as the Fock-Space basis states in this form. Here's an example of how the Fock-Space graph for a spin system looks like, or in particular for this model looks like. And it's basically a high-dimensional graph. And when I say high-dimensional, what I mean is that the dimension of this graph, or the number of nodes, is exponentially large. So the number of nodes is 2 to the power n. And the connectivity is also extensive. I'll come to this in some detail. Now, once I have this model, I can ask that, well, what about this diagonal part of the Hamiltonian? Now I can say that, well, actually, let me not worry about a local model. Let me just assign random energies to each spin configuration. That's what we call a quantum random energy model. And in this case, what happens is that obviously all the Fock-Space site energies are uncorrelated. But then this model is qualitatively different from typical local disordered models, such as a disordered quantum Ising chain, where basically the Fock-Space site energies are very strongly correlated. As a result, this quantum random energy model is not a good approximation for studying any many-body localized phase of matter. And this model, in fact, does not have an MBL phase. Okay, so in the rest of the talk,
yeah, I have a question. So there was this early work by Sthitadhi and all. They claim there is some MBL phase in this model, right? So it's just a finite size effect.
Okay, so the reason we claim that there is no MBL phase in this model is they actually see an MBL phase only at a finite energy density away from the band center. Whereas we already know, or we also know, that the density of states actually has a width which scales as the square root of the number of spins. So what that basically means is that in the thermodynamic limit, the density of states at the energy densities they claim to see the MBL phase goes to 0 or is exponentially suppressed. So if you look at any typical dynamic, suppose you construct some product state and you do some dynamics with it, it will have a large overlap where the density of states is maximum. And there, since there is no MBL phase, you will not see any, say, persistence of memory. So that's why I would say that the random energy model, actually, quantum random energy model, doesn't have an MBL phase.
No, but it is proven based on the Fock-Space argument. I'm saying that, okay, I mean, there is some scaling, of course, but how do you know that it doesn't come into the square root of n, right? I mean, that is based on the argument that you have based on Fock-Space, or is that like proven some other way around also?
Okay, so you mean the fact that that there is no many-body localized phase at the band center?
Yeah. So
that is something that we actually have the self-consistent theory for, but also the forward scattering approximation from Antonello's work also shows that at zero energy density, sorry, not zero energy density, at the right in the middle of the spectrum, there is actually no MBL phase. So the forward scattering also shows that actually.
Okay, and there is a scaling that you can say that it will not come within square root of n of, right? I mean, meaning for finite.
Right, exactly. So if you basically say that I'm going to look at energy densities, then, and suppose this is my critical, or this is my disorder, then what you will see is that it goes as 1 over or the critical disorder goes as 1, let me call this epsilon, so 1 over epsilon. So basically that's the scaling. But since the density of states, once you scale things with energy density, will become a delta function at 0 in the thermodynamic limit. Basically, the fact that you have some mobility edge here doesn't really matter for any generic dynamics.
Okay, thank you.
Okay.
I had a question. So, are you in general restricting yourself to sort of spin systems, or can you also, I mean, for example, this kind of construction is in principle possible for finite U Bose-Hubbard model also, right? But then it's fairly complicated to think of Bose-Hubbard model in this kind of construction, right? Or are you looking at models in general, or you're restricting yourself to like spin systems?
No, so in order for this construction to be tractable, what you need is the local Hilbert space dimension should be finite. So for spins or fermions or hardcore bosons, finite. For bosons, for sort of, for Bose-Hubbard type models, if you restrict the number of, if you restrict the occupancy of the bosons at a given site to some number, then of course you can construct such a model. But if that goes to infinity, then the construction becomes slightly problematic. So what you really need is that the local Hilbert space dimension should be finite.
Right. So that's why I said finite U is going to be difficult. I mean, some infinite U,
Yes.
Bose-Hubbard you can probably.
Yes.
Yeah. I see. So this is okay, fine. Okay, thanks. But is there any? But one can still, think of some truncated setup, and
Absolutely.
and then see that it converges with respect to truncation, or there is still some hope to even.
Right. Exactly. Oh. That you can sort of say that, well, let me put a cutoff on the site occupancy of the bosons, and then see how my result changes as that that is taken to be.
Right. So, and one more thing. So, in terms of numerical advantage, I mean, the complication is the same, right? I mean, there's no compared to what you would get out of exact diagonalization and things like that. Or is there any other trick?
No. Okay. So numerically, there is obviously no advantage, because when you do exact diagonalization, implicitly you are indeed sort of diagonalizing an H-dimensional Hamiltonian. Right. But what this Fock-Space approach does is it allows us to get some analytical handle on this, about which I'll talk in the very last part of my talk.
Okay. Yeah. Okay. Thanks. Yeah.
Make sure. Sorry.
Sorry, Rajesh, go on.
No, just I wanted to make sure I understood one thing, connecting to what you said earlier, when you said like at infinite disorder strength, you have these integrable quantities, which are essentially the site variables. So in some sense, what you is it correct to say that you're expanding around the basis, which would be the eigenbasis at infinite disorder strength, and that's the eigenbasis you're sort of using, and for the diagonal term in the Hamiltonian, and then you want to use this as the sort of starting point for even finite W. Is that right, roughly? Or?
Absolutely. That's absolutely correct. Yes.
So you would, as a consequence, be able to read off these tau z's that you wrote down. If you were to diagonalize it at finite W, you could find the exact corrections to the sigmas. I mean, the taus were equal to sigmas plus these corrections, these correlation. So you would be able to read those off also.
Okay, so there are some ways of getting to these conserved quantities. One thing that I did not sort of mention, which sort of complicates matters a bit, is that these taus, at least for spin systems, these taus also have to satisfy the Clifford algebra, and that actually somewhat complicates the exact construction of these. But there are still some numerical algorithms using Wegener flows to actually construct the precise L bits or precise conserved quantities. Because just diagonalizing is not enough, because if you just diagonalize it, you just get projectors onto the eigenstates. But from that, extracting the local conserved quantities is somewhat more difficult.
Okay. I see. Yeah, and especially if you're doing it numerically. But maybe I'll ask this question when you talk about the analytical aspect. So also just the gamma that you had, that's I should think of as proportional to W.
No, so gamma is not proportional to W. So for example, if I take, say, this model, which I'm going to take throughout the rest of my talk, gamma is going to be one parameter, and the disordered coupling and the disordered fields here would have a distribution whose width would be proportional to W, which is the disordered strength.
Okay. So
and you can think of W over gamma as being the parameter which controls your phase transition.
W over gamma is the parameter that controls the
phase transition. So when W is very large or gamma is very small, you're sort of in a localized phase.
Gamma is the interaction strength, correct?
Exactly. You can think of gamma as the interaction strength, or the term which is affecting the tunnelings between the trivially localized degrees of freedom.
Right. Yeah, thanks.
Okay, so I'm going to talk about this.
Sthitadhi, I have a question. Sure. As a continuation to Manas's. So, do you know how your results scale with the local dimension of the Hilbert space? Or,
no, because we only work with spins or fermions. Yeah.
Okay. I mean, is there any expectation that it would scale out in some naive way?
I think
in the sense of large N or something.
It's tempting to say that, the larger the occupancy or the larger the local Hilbert space dimension gets, the more difficult it will be to localize. So probably I don't exactly know how it would scale. On the other hand, there are experiments on these cold atomic setups with precisely bosonic atoms, which actually show an MBL phase. So I don't exactly know. I mean, now in those experiments, I don't exactly remember whether somehow they restricted the occupancy or not. Okay, so in the rest of the talk, I'll stick to this model, and just sort of keep in mind, just remember that there is a set of terms which couples to the sigma z of the spins, which generates the disorder, and then there is a spin flip term, and I'm working in the Fock-Space basis of sigma z. Okay, so just to sort of give a slightly more detailed view of the Fock-Space graph, as with any other graph, it has a set of nodes, which are all the spin configurations. There are an exponentially large number of them, and there is an on-site energy to each node, which generates the effective Fock-Space disorder. For example, if I take a particular node, let me call it I, then it will have an energy, which will simply be given by this part of the Hamiltonian, where SII is the spin configuration at real space site little I, Fock-Space site capital I. So to formally write it, I'll get something like this. Okay, now you immediately notice that each Fock-Space site energy is a sum of L random numbers. So automatically, if I look at a distribution of this, I get a standard deviation which scales as square root of the system size. So this is sort of an important ingredient that goes into the calculations. And then apart from the nodes, you also have the links, which do two things. That basically tell you that what is the structure of the hoppings on this graph because of the spin flip term. And more importantly, they give you a notion of distance on the graph, because you can say that the distance between, say, two nodes on this Fock-Space graph is the shortest number of, or the length of the shortest path between the two nodes on this graph. That is going to be equivalent for this model to the number of real space sites where the spin configuration is different. So that is basically just the Hamming distance on this graph. And the other thing that follows trivially from this construction is that the connectivity of this graph is actually extensive, because because by flipping a local spin, I can go to an order L number of sites from any given many-body state. Okay, so this is basically the structure of the problem that we are going to analyze. And the specific questions we want to ask is, what is the structure of the MBL eigenstates on the Fock-Space graph? To make it precise, we are going to look at the statistics of their amplitudes. The second question we would ask is, since we have mapped the problem onto a hopping problem on the Fock-Space graph, is there a length scale on this graph? And if there is, then what is the behavior of the length scale near the critical point? And finally, from that, can we say something about the nature of the many-body localization transition? Okay, so in order to extract a length scale, we will define an eigenstate correlation function on the Fock-Space graph. So consider I have an eigenstate psi on the Fock-Space graph, which I have written in terms of the basis states in this way. And let me define a density correlation function on this Fock-Space graph, which I've written as f of r, which is simply the correlation between the density of wave function density on two Fock-Space sites I and k that are separated by a distance r, and basically I sum over all such pairs. Now, a couple of things are useful to keep in mind. That this correlation function has a simple normalization. If I sum over all r from 0 to L, I'll basically get 1, and that comes from the eigenstates normalization. Now, I can equivalently write, once I put a disorder average on all of this, I can equivalently write this correlation function as a product of 3 terms. So let me write it. So it's nh times nr times little f. Now let me explain what these are. So this is simply the Fock-Space dimension. And this is the number of pairs at distance r. So basically nh times nr is the number of terms in this sum. And this nr for the particular spin chain we considered is L choose r, because if I have a system of L spins, there are L choose r ways of picking r spins to flip. And finally, we have this f of r, which you can think of as the average correlation function, or the average correlation at distance r. Now, deep inside the MBL phase, when you are at very strong disorder, you can constructively show that f of r has an exponential decay with some length scale, which I'm calling xi f, f for Fock-Space. And in fact, what you can also show that if you are sort of not at very strong disorder, but still in the MBL phase, the quantity f of r indeed has an exponential decay. That's sort of shown in this numerical picture here. As you can see that if I keep increasing my system sizes, more and more of the data falls onto this exponential curve. So what you then do is you identify psi f as a natural correlation length on your Fock-Space graph, and the expectation right now, and something that you can again show deep in the MBL phase and numerically away from it, is that psi f is actually finite in the MBL phase and divergent in the ergodic. The reason you can understand psi f to be divergent in the ergodic phase is simply by the fact that you can think of the ergodic phase as being characterized by an eigenstate which is uniformly spread over the entire Fock-Space graph. So there is no decay as such, so psi f should be divergent. So once you actually take this form of f of r, feed it into this, and also use the fact that there is a normalization, you basically get a precise relation or precise formula for f of r, which I can write as nr e to the power minus r over psi f 1 plus e to the power minus 1 over psi f to the power minus l. Okay, so this is the correlation function that we are going to work with. Now, before we actually analyze the structure of what this correlation length does, we identify that actually if I look at f0, so recall f of r is defined in this way. So if I look at f0, then I'm basically going to get the self term, which is nothing but sum over I, psi I to the power 4. And this is nothing but the inverse participation ratio, which is often denoted by L2. And this is a rather useful and powerful quantity in the context of localization, because in general, L2 scales as the dimension of the graph to some power minus tau2, where if the eigenstate is completely ergodic, then tau2 is 1. If it's less than 1, it's called fractal or critical, because Anderson states at Anderson transitions actually have this kind of a scaling. And if this tau2 is 0, in the sense that the IPR does not scale with the graph dimension, then we call them trivially localized or exponentially localized. Okay, so if you now sort of take this formula for f of r, then you can actually write down what f of 0 is. So f of 0 simply is 1 plus e to the power minus 1 over psi f to the power minus f. But remember that for us, the Fock-space dimension itself is 2 to the power L, which allows us to write the IPR in this way. So as a result, you immediately conclude that actually this exponent tau2 is related to the correlation length quite simply as this. And this is going to be a rather important equation. So what this now tells you is that if my psi f actually is finite in the MBL phase, then tau2 is less than 1. And that's what I have shown graphically here, that this tau2 is less than 1 throughout the MBL phase, which already is sort of important because this tells me that the entire MBL phase is actually fractal. On the other hand, if psi f goes to infinity, as it does in the ergodic phase, then it tells me that tau2 is exactly equal to 1. And what that basically means that this tau2 is going to get pinned to 1 throughout the ergodic phase. So now, in order to get a handle on the critical properties of this psi f, it's the equivalent question is that what are the critical properties of this fractal exponent tau2? So there can be two possibilities. One is that this tau2 curve actually goes up and hits 1 continuously. In that case, basically what we would have is psi f diverging continuously, consistent with a continuous phase transition. Or the other thing that can happen is that this curve actually goes up here, and at the MBL transition, tau2 is still less than 1, and then it discontinuously jumps to 1. So in order to understand which of this is the correct scenario, what we need is a scaling theory of the MBL transition in terms of the Fock-space IPRs. So what we did was we took this problem and we calculated the IPRs numerically and tried to sort of put them on scaling on universal scaling curves. So let me so this is the result that we get, and let me sort of slowly walk you through the results. So let's first consider the scaling in the ergodic phase. So that corresponds to the data over here. What I have is several disorder strengths all in the ergodic phase, and what we actually find is that the average IPR has a scaling form, which is the average IPR at the critical point times some function which I'm calling fvol. I'll clarify that why in a minute, which is a function of the Fock-space dimension over a non-ergodic volume. We call this lambda2 a non-ergodic volume. And because this is a scaling function, which is a ratio or scaling function of a ratio of two volumes, think of this as the Fock-space, NH as the Fock-space volume, we call the scaling function a volumic scaling function. Now, the physics behind this is, imagine I have my Fock-space. Please do not confuse this with the real space. This is my Fock-space. If I probe an ergodic eigenstate at a scale, which is, or at a volume scale, which is say given by lambda2, what or at scales below that, what I find is that the state actually has fractal scaling over there. But if I zoom out and take a view of the entire Fock-space, then what I actually find is that the same structure repeats over and over again. So what that tells me is that if I'm in the asymptotic limit and my Fock-space dimension is much, much larger than this non-ergodic volume, I have full ergodicity. And as such, L2 goes as nh to the power -1. Whereas if I am too close to the critical point and my non-ergodic volume has become much larger than my Fock-Space dimension, then I basically begin to see the critical scaling. Okay. So from this considerations, what you can basically do is write down the asymptotic scaling forms, and if volume of x has the following form, it's tau2c -1, where tau2c, I should mention that L2c is basically nh to the power minus tau2c, tau2c -1 for x much, much greater than 1, and it goes to some constant for x much, much less than 1. Okay. Now you can ask that, okay, so lambda2 is like a correlation volume. We are calling it the non-ergodic volume. So how does lambda2 behave with the disorder strength? And what we find is lambda2 actually diverges as you get closer to the critical point with an essential singularity. So delta W is the distance from the critical point, and this power alpha is very close to 0.5. So the data for that is sort of shown here. What I have here is log of lambda2 plotted as a function of the distance from the critical point, and you can see the essential singularity here. Now, another crucial point that comes out of this is
one clarification.
Sure.
Why is lambda2 not bounded by nh?
No, lambda2, of course, in a finite system, it would be bounded by nh, which is why if you say for a finite system, you get too close to the critical point, you begin to see the critical scaling. But I mean, lambda2 is like think of it as the equivalent of a correlation length in standard critical phenomena. So the correlation length can diverge at the critical point, right?
So lambda2 is not a sub-volume of the full Fock-Space?
So lambda2, okay, so this picture, maybe this picture is confusing. So this picture is what happens when nh is much, much larger than lambda2. So this is sort of in the asymptotic limit. Okay. If your lambda2 has diverged, then basically what you will see, suppose, okay, let me also draw the picture for that. If lambda2 has diverged, so let's say that this is my sort of nh, and let's say that lambda2 is some scale which is much larger, then within the Fock-Space, you'd basically see only these fractal states. Okay.
What determines lambda2 when it is larger than nh? Can I can I do some computation to find out lambda2?
Yes, I mean, in fact, the scaling collapse is one way of obtaining what the lambda2 is, right? Because you have to find out lambda2 as a function of disorder strength to get this scaling curve.
Okay, thank you.
Sthitadhi, so how large are these systems?
These are still 16 spins. So the Fock-Space dimension is say between 10 to the power 4 and 10 to the power 5.
Okay. But here, let's say if you would have done the like other standard scaling with the second order, I mean, can you distinguish these two? I mean, from
actually, you can. I mean, if you actually try to do a second order scaling, you can see that the scaling is visibly worse.
Okay.
That's something. I mean, in fact, in our model, although we took our model because we understand the Fock-Space of that model better, you can take a slightly different model, such as an XXZ chain. There, the Fock-Space is a bit more complicated because of the conservation laws, but you can do much larger sizes. And actually, this paper also found very similar scalings there as well. Okay, I mean, those are not much larger sizes, but still, around 20, 22 spins.
Yeah, I mean, I'm just asking because this phenomenological RG somehow predicted a huge scale after which you start seeing this KT scaling, right? I mean, somehow here it seems you are able to access it within this system.
Yes, and to be honest, we still sort of don't fully understand why the scaling looks so nice, at least particularly in the localized phase where the scaling looks very nice actually.
Okay, yeah.
Okay, so another sort of, or sort of the last crucial point I want you to take from this slide is, from this asymptotic form of the scaling function, you actually have a prediction for tau2c, because, so remember that here I'm plotting the log of L2 over L2c. So this slope over here basically is tau2c minus 1. And that's actually equal to 0.57. So from this data, we would predict that tau2c is quite close to 0.43. Now, that sort of is giving sort of traction to the idea that this probably goes over and hits a finite value and then jumps discontinuously. But we still need to make sure that that is indeed the case coming from the localized side. And one last thing is that you might ask that, well, what is the effect on the length scale xi f that we had defined? Naturally, xi f diverges in the ergodic phase, and since it's a length scale, a natural scale for its divergence, is the system size. So you can say that xi f goes as gamma L plus some small order 1 correction. What you can actually show by doing or following the algebra between the connection between tau2 and the correlation length is gamma goes to 0 near the critical point with the same power alpha with which the log of non-ergodic volume diverges. Okay, so that's what I had to say about the ergodic phase, and let me go over to the MBL phase now. Now, in the MBL phase, the picture is that, again, let me draw the Fock-Space graph. So imagine this is my Fock-Space. The eigenstates actually live on sort of.
So one question, sorry, regarding this. So then in the standard KT case, you have the scaling for rho s and the correlation length, and their exponents also related. But here you, but they're not same that case. I mean, some alpha prime, but there is some relation. So in this case, you are saying they're exactly same.
Yes, they're exactly the same. Okay, so first of all, that rho s is defined on real space, right? Because that's the
yeah. I'm just saying like a what should I say? It's not, I mean, proper analogy, but I'm saying in the standard KT case, again, you have two exponents, one side of the transition and other side, and there is some universal relation between them, right? I mean, it looks like this is similar, but I mean, again, but you have the same exponents ultimately.
With the same exponents for the divergence of the log of the log.
Oh, actually, there is also same exponent. Sorry. Yeah.
Yes. Right. But the exponent coming from the localized side is going to be different. So there is this asymmetry in the scaling function. Okay. So let me talk about the MBL phase, and the structure there is that on the Fock-Space graph, the eigenstates actually live on a few strands. Okay, and on these strands, the weight or the wave function density actually decays with some length scale psi f, and that's sort of the physical meaning of the length scale psi f. So this naturally motivates a slightly different scaling function on the localized side, and we call it f linear because it's a scaling function of the log of the Fock-Space dimension over some length scale psi, and this is equivalent to saying that log of nh is basically the system size. Now, this psi is not the same as, this is just a disclaimer, the psi is not the same as psi f, and I'll come to that very soon. So then basically you can play the same game. You can ask about the asymptotics of the scaling function, because when you sort of know that when nh is, or rather log nh is much larger than this length scale psi, you have basically L2 being given by nh to the power minus tau2, which of course depends on disorder because the entire MBL phase is fractal. And when this log nh is much less than this length scale, you again basically see L2 looking like the critical scaling. So this tells you that the scaling function or the asymptotics of this scaling function is of the following form. It's e to the power tau2cx when x is much larger than 1. It's 1 when x is much less than 1. And this correlation or this length scale psi actually diverges with an exponent beta, where beta is close to 0.8, and this is sort of a different exponent from what we had on the on the other side of the phase transition. Now, again, looking at the asymptotics of this correlation function, we know that this slope here has to be equal to tau 2c, because again, remember that I'm plotting the logs of the quantity. So what I have from this data is tau 2c is very close to 0.43, which actually is indeed consistent on, and okay, I think this, of course, is a bit of an accident that these two are so close, but the point is that this is consistent with the fact that the many-body localization transition itself is fractal. And what this also means is, since tau 2c, so let me write that. So since tau 2c is less than 1 strictly, that automatically means that psi f at the critical point is also finite. And that's again a strict statement. In fact, again, you can sort of follow the algebra between the relation between this correlation length and the tau 2s, and what you can actually show is that 1 over psi f c minus 1 over psi f is actually equal to 1 over psi, and therefore the correlation length psi f actually approaches its finite critical value with this exponent beta. Sorry, there should be a minus beta. Okay, so let's sort of pull all of this together and see what picture we have. So the picture that we have is that the entire MBL phase is actually fractal, and hence sort of it's critical. The MBL transition is the terminal endpoint of a line of fixed points in the Anderson sense, because this entire line you can think of as a line of fixed points, and the MBL transition itself is the terminal endpoint of that line of fixed points. And finally, the correlation length is actually discontinuous across the transition. So throughout the MBL phase, it's finite. At the MBL transition, it's finite. And then once you move over to the ergodic phase, it jumps discontinuously. And I should mention that on the ergodic side, it's better to not think of a correlation length, but to actually think of a correlation volume, or the non-ergodic volume, which actually diverges as 1 over delta W to some power, alpha, with alpha very close to 0.5. So this essential singularity, along with these aspects of the phase transition, suggest that the phase transition indeed is Kosterlitz-Thouless-like. So with this, we can actually answer some of the questions that we had raised. So the first is, we now understand that the MBL eigenstates on the Fock-space are fractal, and hence they're critical in the Anderson sense. There is indeed a well-defined density-density correlation on the Fock-space graph, which gives you a correlation length, and it's actually discontinuous across the transition. It's better characterized on the ergodic side. It's divergent, and the physics is better characterized by this non-ergodicity volume. And this sort of hints towards the fact that the MBL transition is quite possibly Kosterlitz-Thouless-like, which is also consistent with the predictions of the phenomenological RG treatments. But here you actually get it from a microscopic model. The key was to identify the length scales and the quantities on the Fock-space graph, which can actually show you this. Sorry, how much time do I have?
It has been like an hour and 15 minutes now. So actually, how long do you think that you would need to wrap this up?
Say five minutes, basically.
Okay, that would be fine. Then we can move on to the questions then.
Sure. Okay. So let me very briefly sketch out that the role of the Fock-space disorder correlations that I had sort of hinted towards in the beginning of my talk. So, sorry. So actually, let's now go back to the quantum random energy model and this is a brief digression. So in the quantum random energy model, what you can sort of say is that once you map it onto the Fock-space graph, you have an Anderson localization problem on a graph which is exponentially large in L, but still it's still a high dimensional graph, with a disorder strength which goes as W times square root L, and it has a connectivity of L. Now, this is the closest you can get to Anderson localization on high-dimensional graph. And if you recall what Avuchakra, Anderson, and Thouless had done, he would predict that the critical disorder times square root L should be equal to gamma times the connectivity times the log of connectivity, which tells you that WC is basically proportional to square root L log L. As such, it goes to infinity as L goes to infinity. And this suggests that there is no many-body localization in the quantum random energy model. And this is something that you can show via even more sophisticated calculations. Now, the reason, despite the fact that the disorder and the connectivities on the Fock-Space graph of the disordered Ising chain look very similar, yet it has an MBL transition, is because of the fact that the Fock-Space disorder for these local Hamiltonians is very strongly correlated. Now, the best way to understand that, in my opinion, is look at this energy. In order to fully specify this, I only need to specify order L random numbers, which would be the sets of couplings and the set of fields. Now, if I feed them into my Fock-Space, I basically extract, e to the order order e to the power L Fock-Space site energies. So naturally, the number of random numbers I put into my graph is much smaller than the number of random numbers I took out. So the output is correlated. Or this is equivalent to saying that because if I take two Fock-Space sites which are separated by a distance r, their energies can differ only, or their difference in energies is a sum of r random numbers. So that conditional distribution here has a width which scales only a square root r. That on the scale of the effective Fock-Space disorder, which scales as square root L, actually goes to 0 in the thermodynamic limit as long as R over L goes to 0. So that sort of tells us that the energies of nearby Fock-Space sites are completely slave to each other on the scale of the effective disorder. And to put a qualifier on this term nearby, what I mean is in the limit of L to infinity, R over L should go to 0. This is what distinguishes this problem from a conventional Anderson localization problem on a high-dimensional graph. And we showed that for a whole class of disordered local Hamiltonians, you can actually, in this paper, we showed that you can actually work out what the form of the correlation is. And the form of the correlation precisely has a form, let me write it in this way. The correlation between the Fock-Space site energies at distance r is basically given by W squared times L times a polynomial of R over L. Now, naturally, as R over L goes to 0, as L tends to infinity, rho of R over L goes to 1, because that's the maximal correlation that can be there in the problem. And that's what we call maximally correlated Fock-Space disorder. So what we then did was we sort of took this input and fed it into a self-consistent theory of localization on the Fock-Space graph. Now, in a self-consistent theory of localization, you basically have to average over the disordered potentials. Now, here the technical challenge is that you have to average over a joint distribution, but nevertheless, we figured out how to do that in this paper in two leading order. And what we actually found was that this condition, that rho of R equal to 1 for R over L going to 0 as L goes to infinity, happens to be a necessary condition to stabilize MBL. As soon as you deviate away from this limit, you basically lose the many-body localized phase. The entire system becomes ergodic in the same way as the quantum random energy model is ergodic or does not have a many-body localized phase. So the crucial point is that
just a question. So it's definitely not sufficient, because I mean this condition is even satisfied in higher dimensions, right?
Exactly. That's why. Yeah. No, it's a necessary condition. I don't exactly know whether it's a sufficient condition or not. But the question actually
in 3 dimensions. Also, this is true, but presumably there is no I mean, there's no MBL phase there, right?
I mean, there are arguments for both ways, right? I mean, I personally think that in higher dimensions, MBL is not there, but then it also seems a bit strange that in 3 dimensions, the interaction would be a singular perturbation, right? So, but okay, the latter insight comes from thinking about ground states. But yeah, I don't know. I mean, that's why this condition would be satisfied by disordered local Hamiltonians in any finite dimension.
Right. Okay. Yeah. Thanks. Yeah.
But the question was that despite the fact that the MBL problem looks like an Anderson localization problem on a high dimensional graph, which we know should not have the MBL phase given the scaling of the disorder and the connectivity, why is there at all an MBL phase even in 1 dimension? And there were some recent works which were sort of hinting towards the fact that the MBL phase is itself not present in 1D as well, based on some scaling of spectral properties. But we think that it is indeed present, and at least in 1D, this necessary condition sort of shows that the necessary condition is indeed satisfied by the disordered local Hamiltonians in 1D. Okay, so with that, let me come to the summary of my talk. So I motivated the many-body localization problem on the Fock-Space as an unconventional Anderson localization problem on a complex correlated infinite dimensional graph, and on this graph, you can measure a whole host of density correlations, which tell you that the states are fractal statistics and the correlation length is discontinuous across the transition, which sort of put together suggests that the scaling at near the MBL transition has formal similarities with Kosterlitz-Thouless-like transitions, something also predicted by phenomenological treatments. And finally, I sort of very briefly told you about why, despite the fact that it has scalings of disorder and connectivities, which would a priori suggest that the MBL phase is not there, the maximal correlations turn out to be necessary conditions to stabilize the MBL phase. So with that, I'll thank you for your attention. I'm happy to take questions.
Thank you, Sthitadhi. The talk is now open to question. I know that some people in the audience have a cutoff at 4. So if you have a cutoff at 4, maybe you can just go first if you have questions, and then we can. Otherwise, just as usual, just raise your hand and we can go. Okay, I see one hand, Abhishod.
Yeah, so I think I missed this. You told us that the KT-like scaling explains why the Harris-Chase bounds are violated. Could you explain why?
Actually, no, I did not. So, okay, because let me actually write it here. So the KT-like, okay, so I had this, I had this length scales IF on the Fock-Space graph, right? Now, you can say that, well, how does this say anything about the KT-like scaling? But what I did not talk about is you can show that this length scales IF is analytically connected, as in it's a smooth function of the L bit length zeta. So what that means is that if I were to draw, so suppose this is my disorder strength and I'm plotting zeta, then what I'll find is that zeta actually goes to a finite value at the MBL transition, and it's sort of divergent in the ergodic phase. So because this is now a discontinuous transition in terms of a correlation length or a localization length in real space in 1 dimension, it no longer sort of falls under the Harris CCFS bounds. So it's fine to have, I mean, that's why basically the CCFS bounds don't apply here, because this is not a continuous transition in the language of zeta, if you agree that zeta is a reasonable localization length in real space.
I see. Thanks. Actually, I have one more question. You're talking about in the Fock-Space hopping mapping, you explained how the disorder on that graph was correlated. Is there any information about how the dimensionality is introduced into the correlations? Because presumably, since order L for 1D, the number of random numbers we have to put in our order L, but for 2D, it's order L square and so on. So somewhere I'm guessing the dimensionality would also appear in the distribution of disorder strength.
Yes, yes, and the way it appears is okay. Let me yeah. So one way in which it appears is, I said that this rho is a polynomial, right? Of so one way in which it can appear is that what order polynomial this is of R over L. So, but the thing is that the crucial point is that even in 2D, what happens is, or even in higher dimensions, even as long as it's finite, is it continues to be a function or a polynomial of R over L. So this physics of maximal correlations continues to be there, which is why from this you cannot, from this you would say that even higher dimensions actually satisfy this necessary condition.
I see. Okay. I have more questions, but I'll probably let the others take over for now.
Sorry, it's me too. Abhishek?
Yeah, so I mean, so in this Fock-Space, you have a picture of the phase transition, and so in real space, I mean, is there some I mean, what would one? Is there some correlation that one can measure which actually shows this? I mean, this KT transition. And the other question is, I mean, how is this construction of this Lioms related to this? What you see in this Fock-Space? I mean, is there some connection one?
Okay, so actually the first question is that in real space you can think about a localization length in terms of the L bits, right? So you can say that let's say that tau z I is, let me just write down the first term here, ci mu sigma mu, sorry, j, sigma mu j, and say cj mu goes off exponentially with this length scale, right?
Right. Yeah.
Now, if you say that this is a good localization length on the real space, what you can actually show is that this length scale psi f that I defined on the Fock-Space graph is a smooth function of this zeta.
Okay.
And that tells you that if psi f has this behavior that it's finite in the MBL phase and also at the phase transition, then zeta also has to have the same thing.
Okay, so you can connect these two kind of, there's an analytic theory to
yeah, exactly.
Okay.
Okay, so I cannot construct the L bits precisely. That's something I don't know how to do, at least analytically, but by formally saying that the MBL phase is connected to the infinite disorder phase via a local or by a set of local unit trees, I can actually write down that what formally would be the connection between the localization length or correlation length psi f and the L bit localization length zeta.
Okay.
And Abhishek, you had another question, which is I didn't quite understand it. You said that how
kind of
how do
answers
this?
No, that
Okay.
kind of answers is already. Okay, so there's another independent question. So what happens in like for, let's say, if you have quasi-periodic systems, is the picture still the same, or?
You mean the scaling? So okay, so quasi-periodic systems are sort of interesting, right? Because their the bound is not 2 over d, but it's actually 1 over d, right? Because for quasi-periodic you have the so-called loop bound, and there the exponent has to be greater than or equal, at least in 1D I know that the exponent has to be greater than or equal to 1. So whether the same thing carries over to quasi-periodic systems is something I actually haven't looked at yet. I don't know. So yes, I don't know. I mean, the issue is that the renormalization group arguments, the phenomenological RG arguments, rely on this picture of rare thermal bubbles or thermal regions interspersing your MBL regions, and that comes from the idea of Griffiths regions, that locally you can have regions of very low disorder which act ergodic locally. But we know that in quasi-periodic systems you do not have Griffiths regions. So whether any of this carries over to quasi-periodic systems is actually a very interesting question, but I don't know. On the other hand, you also see some other similarities, like, just in the ergodic phase, but just before the transition, the subdiffusion was attributed to Griffiths regions, but then the same subdiffusion was seen numerically in quasi-periodic systems as well. So there are some similarities, but there are lots of other sort of conceptual dissimilarities, like the absence of Griffiths regions. So I don't actually know whether it carries over one-to-one.
Okay, thanks.
More questions?
Shubhro, can I ask a question?
Yeah, please.
Yeah, so I had one question about, so even if you have long-range interactions, let's say spin chain in 1D with long-range interactions, so you could still do this Fock-Space construction, right? So is there anything known what happens to this kind of fractality that you see for the short-range model? How does it show? What happens for long-range spin systems?
Okay, so I don't, so let me first say what I know. So you can definitely do the Fock-Space based approach for long-range models.
Right.
What changes is how the disorder scales with system size and how the connectivity scales with system size. But all of those can actually be computed analytically. Right. So we did this in a paper. I don't exactly have the reference on me right now, but it's a SciPost paper from 2019, I believe. So what you can actually show there is what we did was an XXZ type model, but with long range interaction. So what we had was something like this. So is this sort of very shorthand notation clear, that the XX plus YY terms had
it's
a decay of alpha?
Yeah, this is what I'm.
So, and here we had an exponent of beta, and then we had a disordered Z term. Okay, so this was the kind of Hamiltonian we looked at. So what we actually found was that if beta is sort of small, which means that your interactions are very long ranged, you actually help the many-body localized phase, right? Whereas if your alpha is small, and by that I mean that your hoppings are long range, then that's sort of the simpler and more expected part, that you disfavor the localized phase. Now, what we actually found was that the nature of the many-body localized phase in these models remains fractal on the Fock-Space graph, but we did not analyze what the sort of precise nature of the phase transition was.
I see. Okay. Yeah, thanks. Maybe one more question. So I think this question has come up in different forms, but so what I'm confused about is, so suppose you have, like, if you have an actual, say, integrable model, Bethe integrable model, like XXZ spin chain, and you calculate, let's say, level spacing statistics. That level spacing statistics basically has the same level spacing statistics as a disordered model deep in the MBL phase, right? It's both Poisson. But now, using this Fock-Space analysis, suppose you calculate what happens to, maybe you mentioned this already, what happens to the fractality? I mean, you can still compute this for the XXZ model, right? Clean XXZ model. Does it have any similarity with an MBL system, or, I mean, are there any aspects of truly integrable models which actually match models which are deep in the MBL phase? I mean, I know level spacing statistics is one example probably, but something more, something like IPR or something of that sort.
Okay, so that actually is an interesting question, and I don't know, because I have never sort of thought about integrable, or in the sense of Bethe integrable models in any detail. But I would, to be honest, I would be a bit surprised if those also show some fractality, because I would have imagined that the states there would be completely delocalized on the Fock-Space on an average, just because there is translation invariance, and there is no sort of a priori, there is no agent for which sort of localizes the eigenstate in any part of the Fock-Space graph.
I see. So
it probably is something even more sort of subtle. Now, maybe in sort of very high moments of it, or in some higher order correlations, I don't know. But just from the IPRs, I would be very surprised if with integrable models like XXZ happen to have fractal statistics. Maybe near the ground state, because I know that there are some, in higher dimensions, there are some ground state frustrated magnet models whose eigenstates do look multifractal on the Fock-Space graph, but probably not for excited states.
I see, I see. So apart from level spacing statistics or something of that sort, there is no real deep connection known yet between true integrable models and MBL systems, right? It's still not clear. I mean,
no, it's not clear to me because I'm not really an expert on true or beta integrable models, but clearly there are lots of other differences, right? For instance, in the notion of how transport and also
sure. No differences definitely, but yeah. So yeah, that's right.
Sthitadhi, just a comment. But I would think that in the integrable case, it depends on which basis you use, right, to construct Fock-Space. In MBL case, it will be robust in that sense, right? I mean, meaning that you can start with this real space, I mean, like K-space basis, and then construct the Fock-Space. So probably integrable case, there will be a huge difference between which basis you choose, right?
But would you say that there is any reason for an integrable model to prefer any sort of real space basis? You know, say sigma z or sigma x. I mean,
No, I'm not talking about that one. Sorry. What I mean is that let's say you write in the K space, right? So in the case starting from the I mean, either you take the real like site basis or the K space basis, then you can construct a Fock-Space. And that I think MBL system will be robust. I mean, depending on whether you choose this basis or that basis for that real space, K space, or some alpha basis or something, it should not matter in the MBL case, but it will matter in the integrable case.
Yes, probably yes. But also, I mean, all the integrable models I know are translation invariant, right? So.
Yeah, that's what I'm saying. So, if probably the translational invariant case will be a special basis for the meaning that if you take some sort of K space basis.
Right. Yes.
More questions? Abhishek, you want to ask?
Yeah. So this is once again following the sufficient condition that you had in the last part of your talk. So there are these. I was just wondering, one interesting question that this could really help us understand is these no-go theorems relating to the compatibility of certain global symmetries with many-body localization. And there are certain global symmetries like non-abelian symmetries with large quantum numbers, SU2 or something like that, which are believed to destabilize MBL. Can one reproduce those theorems? A, can one reproduce those theorems using this sufficient condition? And B, there are certain uncertain cases like finite non-abelian symmetries and things like that. Whether this could say, like, the sufficient condition could say anything about the stability of those phases.
Right. Actually, so this is something that we are sort of thinking quite actively about, and probably you already know that one way in which you can go about doing this is something called a spectrum bifurcation renormalization group. I don't know if you know, but so basically what you do is you write down your Hamiltonian on the Fock-Space graph in terms of sets of polystrings, right? And then basically you ask that which polystring has the largest coefficient, and then you write down your Hamiltonian in the eigenbasis of that particular polystring. So that becomes block diagonal, and you take care of the off diagonals by a standard Schiffer-Wolf. So that basically keeps sort of segregating your Fock-Space, half of it at a time, and then the RG flows in that sense. And then you start asking about the distributions of the couplings. So
this is a trick to generate the distribution of couplings, the correlation, the extra correlations from symmetry, the couplings.
No, I mean, this is basically, you can think of it as some sort of a strong disorder RG, but done on the Fock-Space graph. And the reason we want to do it is this way is then you can do sort of very large system sizes of maybe a few hundreds spins. Now,
but this is a different approach from the Fock-Space graph thing, right?
No, not really, right? Because it basically, no, because what it does is it breaks your Fock-space into two at every step. And yeah, and then basically you ask that what is, then the questions that you ask then are very similar to what you would ask in the context of strong disorder RG, that where does the RG flow in terms of the couplings, and I mean where does the of course the question here is complicated because you cannot just talk about the couplings on the Fock-space graph, because you have to talk about them as in you have to talk about the flow of the joint distribution because of the correlations. But that's some, yes, I'm sorry, I'm probably not being very clear, but that's
actually can I let me simplify my question. So is there a condition that we can introduce on the polynomials and study how that would affect whether the sufficient condition is satisfied or not? There's a polynomial G that you wrote down. Yeah.
So if it so happens that I see, okay, so if it so happens that this has a feature such that this does not go to 1, then of course my claim would be that you don't have an
exactly,
MBL space.
My hope is that like using the like they'll probably be introduced into this polynomial using Clebsch-Korn coefficients or something, and that should
okay, yeah, that's the direction I haven't thought about, at least in the context of these absence of MBL with non-abelian symmetries and so on. But yeah, that's something that's interesting to think about. Yes.
Okay, thank you.
Okay, more questions? Okay, there seems to be none. So thank you, Sthitadhi, once more. And thank you on behalf of everyone for both the talks. And so Sthitadhi is virtually going to be around for the rest of the week. So if you want to have a chat with him, just drop me an email and I'll try to patch up sometime. Okay, so thank you, Sthitadhi, and see you for the rest of the week. Okay. Bye.
Yeah, thank you. It was a pleasure. Yeah.